Hi, welcome back. See how I've changed the title? Modulus-Argument form. What we do is we work out a complex number in Modulus-Argument form. Okay, so we can see that a complex number is like that, and we use x and y now. So z equals x plus I y. That's what we call Cartesian form. Okay, Modulus-Argument form means writing like this: z equals r cos theta plus I sin theta, where theta is the argument, r is the modulus. Okay, so that's why modulus and argument are pretty important, because it helps us to write them in this form. Okay, so what I'm going to ask you to do is to work out the modulus and argument of that for me. Pause the video and then do it. Okay, did you draw an argument diagram? Hope so. So that's going to be negative root 3, 1. Okay, and of course what we want is the argument is going to be that. So if we work out that angle there, yeah, then we can actually do it. So that's going to be what? Root 3, 1. Let's write down the modulus first. That's pretty easy, isn't it? I'll tell you what, I've not actually used this, have I? This is the shorthand notation for modulus, which you should know anyway from mechanics work and vectors work. Okay, but I'm going to do that. Okay. Yes. Okay, but I'm going to write it down like that just for this example. So that's going to be 3 plus 1, which is 4, and the square root of that is 2. Okay, and then argument of z, because this is, right, you can write r equals theta equals if you want, but this is just nice notation as well. Okay, so that's going to be, so we'll do that, pi over 2, added to whatever that angle there is, and that's going to be the inverse tan of root 3 over 1, which is inverse tan of root 3. Okay, and inverse tan of root 3, pi over 6, yeah. No, pi over 3. Yeah. Inverse tan of 1 over root 3 is pi over 6, isn't it? So it's going to be pi over 3. Sorry for that. No harm done. And then this plus this, so 3 pi over 6 plus 2 pi over 6, 5 pi over 6. Yeah. So, yeah, modulus and argument. Okay. So what that means is, in modulus argument form, you can write down this complex number as z equals 2 cos 5 pi over 6 plus I sine 5 pi over 6. Done. And that's the same as that complex number, just written like this. Okay. Before I move on a little bit more, because I'm not going to talk about this in great depth, you can convert between modulus argument form and Cartesian form very, very easily. Very easily. It's always easier to convert from there to there. Let me just demonstrate how. Just work out cos 5 pi over 6, times it by 2, you get that, don't you? Work out sine 5 pi over 6, times it by 2, and you get that, don't you? 1 i. Simple. Okay, simple. Converting from this to this, well, we've just done it. We've just done it. We just found the modulus and argument of that. So it's very easy to convert between these two. Very, very easy. But easier to do that because you just type in your calculator and away you go. Right, what I'm going to ask you to do is this. Okay, I'm going to ask you to work out the modulus and argument of that, the modulus and argument of this. I'm not going to give you difficult complex numbers. There's no point in making them silly. Okay, so simple complex numbers. Modulus and argument of that. Modulus and argument of that. Then I'm going to ask you to find this, the modulus of z1, z2. That's the modulus of z1 times z2. And then the argument of this z1 times z2. The argument of z1, z2. Okay? Can you do that for me? Great. I'll see you in a bit. Okay, done. Good. Right, so let's get going on this. Okay, so I reckon for the modulus of z1 you had 5, and for the modulus of z2 you had 4 plus 4, 8, 2 root 2. Yeah? I'm hoping so, otherwise you're checking your answers. So I'm fairly certain that I'm right. So argument of this, 4 over 3, I have a calculator which I brought down specially for this reason. Okay, so I can't memorise that one, see. Inverse tan of 4 over 3. So that's okay, 0.9272, yeah. 0.927 ... Mamma mia, mamma mia. There we go. Argument Z2, 2 over 2, 1, pi over 4, isn't it? Yee. So you should have had those. Okay. Now, modulus of Z1, Z2. I reckon what you did was you did that times that, then found the modulus. Yeah. And same for that. Once you had that times that, you found the argument. Yeah. There's a quicker way. There's a quicker way. Yeah, but this is the point of this example. You see. So I reckon for the modulus Z1, Z2, I reckon you got this. Alright? Yeah. So what's the quick way of doing it? You can probably see, can't you? Yeah, exactly. This is a general rule now. Okay? This is a general rule in writing. All you need to do is multiply the moduli together. Plural of modulus, moduli. Okay? So Z1, Z2, you multiply the moduli together. That's all you're doing. Okay? Because a modulus just stands for length. Okay? Yeah, and so you just get 10 root 2. Can you see what I'm going to do next? I'm going to tell you a simple way of doing arg Z1, Z2. Can you beat me to it, or do you just want to pause the video and see what the result is? I'm going to type that meanwhile. I kept that in my calculator display. Our news is coming up. So, can you see what buttons I'm pressing? Yeah, 1.712. I did that plus that. Okay, it's argument of Z1 plus argument of Z2. I can just about squeeze it in there. 1.712 ... Yeah, which is quite a handy result, isn't it? Yeah. What does that mean mathematically? It means when you've got two complex numbers and you multiply them together, you multiply their lengths together, and you add their arguments together, which is quite a cool result. Okay. What about if you're dividing? Can you just have a think about that for me? What's the result there? Very good. You just divide the moduli together. Check it works in your example. You know, if you worked out Z1 multiplied by Z2, you can work out Z1 divided by Z2, but it's a bit harder because you've got to do the realifying of the denominator. It's not really a term, realify, but you know what I mean. Okay. Yeah, that works. Okay. And this one, what you're doing? Yeah, you're subtracting the arguments. You're doing the opposite, aren't you? Okay. So you subtract the arguments together. Yeah, so that's that. Okay. That's rather handy rules. Okay. Now, got all that? Great. I'm so glad you said yes. Let's do one more example, I think. Okay. Right, I'm going to get rid of this. I'm going to call that Z1. Okay. And Z2, what can we have? What can we have? I don't know, let's just have 3. I'm writing in modulus argument form, you notice. Okay. Cos pi over 3 plus I sine pi over 3. So that's Z1, that's Z2. Okay. What I'm going to ask you to do is do this for me. Work out Z1 times Z2, Z1 over Z2. And think about the rules that we just talked about. Okay. See you in a minute. Okay. So for this, Z1, Z2, okay. When you simplified it, did you get 6 as your modulus? I jolly well hope so. Because the modulus of that is 2 and the modulus of that is 3. So, you know, the rules of multiplying the moduli together, 2 times 3 is 6. Open up the brackets. What did you get for your argument? Okay. Did you do that plus that? I jolly well hope so. Because the argument of that is this, the argument of that is this, And so the argument of this times this, you add them together. Okay, so it's the only difficult bit you've got to do. So what's that? 2 pi over 6, 5 pi over 6, so 7 pi over 6. Okay. And incidentally, you know that that angle is always the same as that angle. Here, you see, these two have got to be the same angle, otherwise it's not in modulus-argument form, because that stands for the angle between the complex number and the real axis, right? Yeah, so that's that. What about for z1 over z2? Maybe just pause the video and just think it over. Okay, so did you get this? 2/3? Again, I hope so. So just divide the moduli, okay? And then open bracket, cosine. Did you do this? Subtract this? Yeah. So what did I say? That was 2 pi over 6. Notice common denominators are best. So 3 pi over 6 plus pi over 2. Okay, plus I sine pi over 2. Done. Okay. So can you see when you write it in modulus-argument form, it's so much quicker to multiply and divide complex numbers together. So much quicker. Because all you've got to do is just multiply those two numbers, add those numbers, or divide that by that and divide and subtract that from that. It's so much quicker. So, yeah, one of the really good reasons for using modulus-argument form.